So, welcome to the lecture on mathematical modeling. In this lecture, we will discuss the modeling of rotational mechanical system. So, in the previous lecture, we discussed about translational mechanical systems. So, the system that has translational degree of freedom. In this lecture, we discuss rotational mechanical system is the systems that they have the rotational degree of freedom. So, these rotational systems will be solved in the similar manner as we did the translational systems. Only here the rotational degree of freedom will be used, so that the translational displacement will be replaced with the angular displacement and the torque will replace the force. We will, to solve the systems, we will write the equation of motion by using the Newton's law on the free body diagram of the system. And then we will take the Laplace transform to find the transfer function of the systems. So, let us take one example of rotational system. So, we can see here this is our system. So, here this damper is a damper that responds to angular velocity, and here is the inertia. Now, in spite of mass we use inertia that is subjected to some torque T, and angular displacement is theta 1 for this first inertia. Then there is the spring. This spring is responsive to the angular displacement, and this second inertia has the angular degree of freedom, the rotational degree of freedom theta 2t, and there is the second damper attached to this second inertia. So, this system we can write the differential equation of motion, and then we can solve to find the transfer function. So, here is this system. So, this is inertia J1, this is J2, this is damper with damping coefficient D1, this is D2, and here is applied a torque to the first inertia T, that is function of time, and the degree of freedom theta 1t, and here is theta 2t. This spring has stiffness K. We have to find theta 2 s by T s. This is the transfer function we have to find. So, we have to find this theta 2 s and this is T s. So, input to the system is the torque and output is theta 1 and theta 2, but here we are interested to find this transfer function theta 2 s by T s. There is also possible to find the transfer function theta 1 s by T 1 s in the same manner. So, now when we want to find this transfer function, again we have this 2 degree of freedom system, and we will make the free body diagram and we apply Newton's second law in the rotational degree of freedom, and then we find the differential equation of motion of this system. So, let us say first this mass, this inertia J1. So, this is J1. So, this J1 is, suppose it has this theta 1 double dot, this angular acceleration in this direction, and the torque is applied here in clockwise direction. Now, this damper will apply the force in opposite direction. So, in anti-clockwise, so this is d1 into theta 1 dot, and this spring is between the two inertia. So, the difference of the two theta 1 and theta 2. So, again it will apply in anti-clockwise k theta 1 minus theta 2. The second inertia J2, this is theta 2 double dot, this acceleration, angular acceleration. This damper will apply a force opposite. So, d2 into theta 2 dot, and this spring will have the force, we can say k times theta 2 minus theta 1, or this can be, if we take the same this direction, we can write k theta 1 minus theta 2. So, here we are applying opposite. So, k theta 2 minus theta 1. Now, we have shown the free body diagram. Now, we will apply here the Newton's law, that will be j theta double dot equal to summation of torque. So, j is the inertia, moment of inertia, and theta double dot is the angular acceleration. So, this is equal to summation of the torques. So, for the first inertia J1, we will have J1 theta 1 double dot and these torques. So, we have this torque T, external torque, that is input, then these are the torque due to this k minus k theta 1 minus theta 2 minus d1 theta 1 dot. So, we can write j1 theta 1 dot double dot plus d1 theta 1 dot, and here minus k theta 1, this will go the other side, that will be plus k theta 1, and here is minus minus plus, go other side, minus k theta 2 equal to T. This is equation number 1. Now, for this system, we write J2 theta 2 double dot equal to summation of torques. So, minus d2 theta 2 dot minus k theta 2 minus theta 1. So, we can write J2 theta 2 double dot plus d2 theta 2 dot plus k theta 2 minus k theta 1 equal to 0. This is equation 2. So, we have find the differential equation for both the inertias. Now we have to find the transfer function. So we have to take the Laplace transform of both the equations. So let's take first this Laplace transform of these equations, and because objective is to find the transfer function, let's put all the initial conditions 0. So here J1, this is second order, so S square and theta 1 S plus d1, this is first order differential equation, differential term. So this is S and theta 1 S plus k theta 1 S minus k theta 2 S equal to T S. So we can simplify this. We collect the terms. So we can write J1 S square plus D1 S plus K theta 1 S minus K theta 2 S equal to T S. So this is equation number 3. Now we take the Laplace transform of this part. So this is J2 S square theta 2 S plus D2 S theta 2 plus K, so here S theta 2 S minus K theta 1 S equal to 0. This is equation number. So we can write this equation in this form: minus K theta 1 S plus J2 S square plus D2 S plus K theta 2 S equal to 0. So this is equation number 4. Now this equation 3 and 4, we can apply the Kramer's rule to find the this transfer function. So Kramer's rule, as we saw, we can apply. So if our delta is the determinant, so here J1 S square plus D1 S plus K and minus K, and here minus K, and this term J2 S square plus D2 S plus K. This is delta. Now we have to find the theta 2s. So theta 2s equal to this, this is delta in the denominator. This term will be, this will be replaced with the column of the this side, the right side, that is Ts and 0. So here this J1 S square plus D1 S plus K, here minus K, and this is Ts and here is 0. So 0. So we should understand here, we should differentiate. So this column is same, and because we are finding theta 2s, this column will be replaced with the column to the right hand side term, that is Ts and 0. So from here we will find this equal to, now this is 0 minus Ts into K, so minus minus plus, so Ts into K, K by delta. So from here we can find that theta 2s by Ts equal to K by delta. So, this is the transfer function theta 2s by Ts. So, here it is k by delta, and delta is given with this determinant. Now, you see that this transfer function contains the parameters of the system J1, D1, K, J2, D2, and so this transfer function shows the characteristic of the systems. So, this is how we can find the transfer function of rotational systems. Now, we have some discussion on impedance. We can represent the impedance of a mechanical system. So, the impedance of a mechanical system is represented as the force upon displacement, that is in the S domain. So, for example, for the inertia, we can see from this in this slide, this inertia that is subjected to torque and theta, there is the theta degree of freedom. So, we can write torque equal to J into d square theta by dt square, and so Ts equal to J into S square. So, here torque equal to J into d square theta by dt square. So, here Ts we take the Laplace transform. So, equal to J into S square into theta S. So, Ts by theta S equal to Js square. This is called impedance of the inertia. Similarly, for the rotational damper, we have torque equal to d into d theta by dt. So, here Ts we take the Laplace, so d into s into theta s. So, this implies that Ts by theta s equal to ds. For rotational spring, we have torque equal to stiffness of the spring into theta. So, we take Laplace, Ts equal to k times theta s. So, here Ts by theta s equal to k. So, these are the impedances of a mechanical system and defined as the torque upon the displacement or force upon displacement for the translational system in the S domain. So, now, we come to the another mechanical systems. They are more applicable in mechanical components, that are the gear trains. So, because gears provide mechanical advantage to rotational systems, and so they find frequent applications in several applications. So, we can understand how we can represent the impedance of gears. How can we find a transfer function that contains gears? So, if we have two gears here, so these two gears, they have radius. Because these two gears are attached on different shaft and they have the different radius. Suppose this shaft applied with the torque T1T and there is the angular displacement, angular displacement theta 1 t, and it has a number of teeth n1. So n1 is the number of teeth on this first gear, and so this is gear 1. So here we are giving input. Now this is gear 2. So gear 2, it has number of teeth n2, and torque on this shaft is coming as T2, and angular displacement is theta 2. So as we know that on the circumference the same displacement will be traveled by these both gears because they are in contact. So R1 theta 1 will be equal to R2 theta 2, and so here we will get theta 2 upon theta 1 equal to R1 by R2. Here R1 is proportional to the number of teeth, and R2 similarly proportional to the number of teeth. So R1 by R2 equal to N1 by N2. So this is expression, second expression. Now if we assume that these gears there is no any energy dissipation, so this is an assumption. So the energy coming to the input will be same as we are getting to the output. So we assume a loss, no loss in the gear. So energy in to gear 1 equal to energy into gear 2, and energy can be represented as torque into the angular displacement theta. So T1 theta 1 equal to T2 theta 2. So we will find T2 by T1 equal to theta 1 by theta 2, and theta 1 by theta 2 equal to N2 by N1. So this is equal to N2 by N1. So we can represent it like this. So input torque T1 and output torque T2, and this is the transfer function, that is N2 by N1. Here is theta 2 and theta 1. So output angular displacement theta 2, and this is theta 1. So see theta 2 by theta 1 is N1 by N2. Now we take another example here. So let's take one example. We can see here the example. So we have one damper, spring and inertia, and here is input shaft there is a gear that contain n1 number of teeth, and input torque T1 is applied here, and there is the input angular displacement theta 1. Then here is gear 2, that is on the second shaft. There is inertia, damping and stiffness. So here we can express this system. So because we know that T2 by T1 equal to N2 by N1. So here we know that T2 by T1 equal to N2 by N1. So the torque can be represented here on this shaft, this T2 and theta 2. So T2 equal to T1 into N2 by N1, and this is J, this is D, this is K. So we can write the equation like J S square plus D S plus K theta 2 S equal to T2 S, and that is equal to T1 S into N2 by N1. This theta 2 S we can write here theta 2 S equal to theta 1 into N1 by N2. So Js square plus ds plus k theta 1 S into N1 by N2, and that is equal to T1 S into N2 by N1. So here we can take this here. So this will be N1 by N2 square. So J N1 by N2 square S square plus D N1 by N2 square S plus K N1 by N2 square equal theta 1 S equal to T1 S. So here the theta 2s by T1 S we can find N2 by N1 upon this term Js square by plus ds plus k. We can also find here this transfer function theta 1 S by T1 S, and that will be this term. So we see that N1 by N2 square is multiplied with these impedances Js square, ds and k. So we can shift the impedance of gear train to find the transfer function, whether we are interested to find the transfer function theta 2 s by T1 s or theta 1 s by T1 s. And we can represent here, we can see that we can represent this system as we transferred the impedance of the gear train as well as this system on the input shaft. because here this input shaft subjected to torque T1 and the angular displacement theta 1 t, and the impedance of these components on the second shaft as well as this gear train, all these impedances are transferred to the input shaft, and this is the system we can represent like this. So here this input shaft is the destination shaft, and here we see the rotational mechanical impedances can be reflected through gear trains by multiplying the mechanical impedance by the ratio number of teeth of gear on destination shaft upon number of teeth of gear on source shaft square. So here we are representing to the input shaft, and so the input shaft is the destination shaft. Therefore, we are doing n1 by n2 square. Here we have multiplied and we have shifted this input impedance to the input shaft. So that's how we can handle the rotational systems and gears, and we can write the equations and we can write the transfer function for these systems. So I thank you for attending this lecture, and see you in the next lecture. Thanks.